second, just terms. We got some new definitions that are very simple, but not everybody remembers them, and so then we speak, language, and you're like, what are you saying? So, can we start? Let's make some coffee. Got it happening in your head. You're like, oh yeah, I got the coffee. Put it in the filter. Water comes through, and all of a sudden I got the glorious devil's brew there, right? All right. Is that good? Anybody need coffee? Did I make you? Okay. So, what do we call the coffee grounds themselves? Solute. Yeah? Then what would you call the water? Solvent. And then what would you call the coffee? Solution. Okay, so those are good terms. You got that all right? Okay, cool. We got all that. We did talk about just some basic parameters for getting solids and gases into solution, just so you kind of have a clear understanding. I think everybody's pretty clear that when I need to dissolve a solid in water, do I want to heat? Show me with your thumb, up or down? Does that make sense? If I heat it, it's more soluble. Of course, in here we saw that there is a weird salt floating around the world that actually does the opposite. But that's just a side note. Like, I doubt any of you are putting cerium sulfate into any. I hope. Probably not. Okay. Is that all right? What about gases? I want to put more gas in water. Which way would I go? Heat it up or cool it down? You actually cool it down. Yeah. So, that just has implications, especially for environmental stuff. The Platte River flowing through town, as it starts to lose heat, then we're worried about the fish life in there because they can't breathe, because they can't keep the oxygen in the water. So that's a bad thing. That's why bodies of water, when they start to heat up, sometimes things start dying. If they're air breathers in the water, right? Air breathers. Yeah. Okay. What about impertinent to gases as well? If I want to push a gas into water with pressure, should I increase the pressure or lower the pressure? Increase? Lower? What do you think? Think about a soda. Is that under pressure or is that no pressure? What's your thought there? Pressure, and that helps put the gas in, right? What happens the minute you release the pressure? It comes out, yeah. So increased pressure will push gases into fluid. So that was just generic stuff that I think is important for solutions. That's just good for your understanding. All right. So then we started working on this new measurement. We're going to learn a couple units, at least one. I'm going to throw another one at you that's not on the slides, but I just want to. We've been in conversation with the dental hygienists, the program, and we've been talking about curriculum, and we've been doing this for a while. I had this in my lectures early, then I pulled it out. Now they're like, yeah, you should have that back in there. Okay, let's get it settled here so we can kind of be consistent on our end. But the first one we talked about already, so let's get that right. That's molarity, right? That's what we've kind of ended on. We didn't do much calculations, but we got it started. Who knows the symbol for molarity?
Capital M.
Capital M. Has everybody got that? All right. And what does that represent in terms of concentration? I've got a 4 molar solution of sodium hydroxide. And then that implies already this, right? What does that symbol mean?
Aqueous.
Solution. And what's the solvent when you put that in water? That's something dissolved in water, correct? So what does this mean? You have 4 moles of, what's this called? Sodium
oxide. Or
hydroxide. Okay, that's sodium hydroxide in every. Okay, do that. There's 4 moles of sodium hydroxide in. Finish. That's not much of a concentration. That's how much, right? How many? Yeah, in 1 liter of
solution.
solution or solvent. it is certainly solution. Don't get that. That's one that throws students off. So that means 4 moles. Now watch, here's the new, that's an abbreviation, not the same, right? This is a concentration, this is how many pieces. And this is a weird abbreviation because it's abbreviation of this. Whoa, save me loss, econ that, right? Right, it's how many, right? There's 4 moles. Remember how we did that? It's 6.02 times 10 to the 23rd. It's a boatload of atoms, right? I have 4 of those. We're 24 times 10 to the 23rd, roughly. Sodium hydroxides in every liter of the solution. This is the solution. This one is for sure. Right? So it means if I had a liter of this, it has 4 moles of sodium hydroxide. Good stuff? Perfect. So now we're kind of getting ready to start moving into some of the math, and that's kind of where we left off. So what does a half mole of calcium chloride mean? Half a liter?
Half a mole.
Half a mole, which you might go, well, how could you have half a mole? Remember, a mole's a boatload of stuff. So it's like 3 e to the minus 23, right? It's half a mole of atoms of calcium chloride dissolved in
Solution.
in a liter. See, it's always per 1 liter. That's the relative concentration. Doesn't mean I have a liter of the stuff. Just means if I did have a liter of the stuff, we'd have a certain concentration. This is a good example. Can I pick this up here? Everybody see this? This is a good example. It started off a liter, yeah? But once she cuts it down, it's still the same concentration. So if it was, in terms of electrolytes in there, which means what? Salts, right? Now we learn that, oh yeah, it's just salts, right? Salts that my body needs. In terms of those, the concentration's not changing even though she's drinking it. It's just, how do I describe it? So if it's made 2 molar electrolyte, 2 moles of electrolyte per liter, if it was made that way, when she drinks it down, it's still 2 molar per electrolyte, right? It's just I may not have a liter. So I have less moles. Correct? Don't overthink that. I'm just trying to say concentration is always relative to a liter. That way we have a relative point of reference. But we'll do more with that, and that'll make sense. Now, I could also say that many moles per 1,000 mils, right? A liter's 1,000 mils. So I can use whichever. If that helps you, and you'll see why. All right, got all that. All right, now we're going to do something with it. We're going to start some math. And this is where I was like, yeah, I better get you out of here because I was working you too hard the other day. We'll pick up now, though. We're back. We're fresh. Okay, so what we're going to do is now start doing some calculations. So I want you to be thoughtful of why. You know, I might care about this. Let's say I have a reaction that needs the chloride. And I'm thinking about sodium chloride for a second, so I'm just trying to think if I can even think of anything, but I can make something. So let's just say I'm going to do some sort of chloride addition to something. My brain, I'm trying to get you a legitimate one. I'm like, wow, that's a stretch. Sodium chloride is fairly unreactive. If I could turn it into something with chlorine gas, I could probably do it. So I am using electrons from oxidizing the I don't know. I'll just make something. Pretend this is true. It's not. There we go. Let's make it up. You ready? First off, here we'll do this. This is just for fun because I need to kind of get you back through this again because I want you guys thinking about this. Do you remember when we started this early, we were actually learning how to balance these? We made sure that you didn't have atoms showing up that weren't really there. Do you remember that? In other words, I have how many chlorines in this structure? How many do I have in this?
3.
So I have 3 came out of nowhere, or 2 came out of nowhere. That doesn't make any sense, right? So remember, if the formula's right, I can get in there and balance it to make it correct. Remember how to do that? I'm just going to run through that because we're going to do a little bit of that in the next few lectures. Okay, we might hit it again after spring break. I just want to remind you of this technique build. Okay? So the first thing I do is I make sure my formulas are correct. And nothing's diatomic in here, right? You wouldn't know this unless I told you it's iron 3 chloride, right? You can't just predict that because it could be iron 2, it could be iron 3, we don't know, right? Because of its transition. But this is correct. So now we're ready to balance it. Can anybody help me? What do I do?
You can add 3 to the
Add 3 here because as I start I say, oh, there's not enough. And I never put a change down here. I always put it there because I don't want to change the structure, right? That is what it is. Then what do then I restart. Now what do I have to do?
Add a 3 to the Na on the other side.
Have to add 3 to the sodium. Is everybody happy now? Good? Okay. So my point is, because we're back to solution chemistry, I'm going to have my sodium chloride in terms of this concentration. I have it. These are in terms of moles. Right? There's 3 moles plus 1 mole makes a mole plus 3, right? So I need to deliver so many moles. So I'm going to change this problem for just a second, just because I want to make it relevant, so you guys get why I care to do this. Right? So I'm going to say, hey, I need 3 moles to put in here. And what I got is 2.5 molar. So how much should I pour in? Now do you follow the problem? Like the solution has 2.5 moles in every liter. So if I poured in a liter, I wouldn't have enough, because how many do I need? I'm 0.5 short, right? But I need 3 total, correct? So I got to somehow adjust to pour enough in to get my 3. Agreed? So that's where I'm just trying to say, this is why these techniques are important. So I'm going to go over there and go, I need 3 moles. And then the magic sauce for all solution chemistry is use your concentration units as conversion factors. Use your concentration units as conversion factors. What do you mean? Well, you just told me the definition of 2.5 molar. That means 2.5 moles of sodium chloride per 1 liter. Oh, okay, there's my conversion factor. So, yeah. That's the true question. There you go. Tracking now? So, I got to get 3 moles. This is now a conversion factor. Can anybody see how I can put that in so it would cancel moles of sodium chloride and leave me liters? What should I do? 2.5 moles at the bottom. And then the 1 liter at the top. And it does what I want because it's going to give me what? What kind of units? It's going to give me liters. It's going to give me a lot of blue on my hands. That's what's going to really do. Perfect.
Is this based off this question right here?
No.
Oh, okay.
I'm just trying to get, I was going to go into this question, but I was like, I just got to make this relevant. Like, why do I care to find moles out of concentration? Because when you have problems like that, everything's in moles. Right? When you have a balanced equation, everything's in moles. So sometimes I got to know how many moles to deliver out of a solution. Right? So with that in mind, what do you get? By 2.5 and you get? You guys have calculators, right?
Yeah.
Yes, okay, drag those things out. Remember those? Yeah, we're gonna use them. We're gonna use them today. I should have said that earlier. Just use your phone, it's fine. And remember, you guys can turn your phone sideways at the side too, right? I think. Cool. Is that right? 1 point how much? 2. That divided by that should be under 3, right? Makes sense? Better?
Yeah.
Cool. Follow that. All right, let's go to the board now. What volume of 2.5 sodium chloride is required to deliver half a mole? All right, you guys work on it for a second. Everybody see if you could do that. Same idea. The part I now know, half a mole, correct? And then it says how many, what volume? So the easy thing here is I'm going to probably turn that in liters, right? Simple. And then again, always use your concentration as conversion factors. Don't try and write this in there because that's no use to me, but if I write it as 2.5 moles per liter, I now have what I need, right? Start using that in the units it is. Right? How should I put this in here? What goes on the bottom? Half a mole? Half a mole on top or on the bottom? Or 2.5 on the top or the bottom? 2.5 moles per what's on top then? 1 liter, because that's a fact, right? I do that math and I get how many liters? 0.2 liters. Easy enough? I did it in milliliters. Doesn't matter. 200 milliliters is 0.2 liters. Everybody agree with that? Do it either way. Now let's do a little variation. Now I'm not telling you how much, I'm not trying to get so many moles, I'm just saying, hey, I got 75 liters of this stuff. Right? Now I'm trying to figure out how many moles would come out of that total. Where do I start? Start with what you have, right? What's the amount you have? 75 liters, good. Start with that, 75 liters, that's what I have. It's a lot. Then I'm going to use the conversion factor, right? I'm not going to put big M in there, I'm going to put, so now what goes on top?
0.5.
Yeah, there you go, 0.50 and then units. MOL per liter. And we might as well use liters here if we want that canceled, right? Answer? Oh, that sounds pretty good. And the units? There you go. That's what cancels. This is out. Follow? Okay, I'm going to show you another one. I'm going to show you, like I said, I'm going to do 2 units that were already part of this. I'm going to expand it with just 1 more, and then you have 3 units to mess with. The thing I really like to help students out with is we sometimes do this as science teachers and no one ever goes, why do you have different units? Like, just stick to one, right? But the fact of the matter is, for you working people, right? You have units that are kind of stuck to your trade. Malaria is probably not one of them. I doubt you've ever walked in a dental office and said, oh, here's a concentration of some, mouthwash or whatever, and you have molarity. You're like, I don't even know what that is, right? That's the chemist's favorite, so we got to show you that. That's how we roll. We roll in moles. But this is probably more realistic to you, and then the next one I'm going to show you is parts per million. That's the one that has come up that people need to be aware of. But this is a very common one because it's kind of, excuse my language, but it's bastardized. It's very weird. It's a percent concentration. And I tell you this, if you're in the medical field and you say something percent is going to be administered or whatever, they're probably using this. And what it is percent, it's mass per volume. So it's very strange. That's why it's strange. Because think about this. Mass is not the same thing as volume. You tracking with me? Mass is not volume. It happens to be the same in water. And most of the stuff you're working with is water type based materials. So that's why that transition happens. But I just want you to realize why this mass per volume shows up. If I'm administering medicine, for example, like I need some painkiller, and it's coming in a fluid shot, the amount of painkiller I need is based on my body weight, and then I need so many grams or milligrams based on how much I weigh. Everybody with me there? Okay. But if the material's been dissolved in water, now I'm dissolving it, and so now I'm administering so many mils. So that's why we have a mass, which is the mass of analyte per mils of solution. But percent always means per, does anybody know? This is just a math concept. Per 100. So if you remember percent always means per 100, you'll remember this. That really, whenever I see percent in the medical field, so you might hear like, okay, I need a 0.125%, ibuprofen. I don't know if I can spell it. There we go. It's not very much, right? I can immediately jump to this. Remember what I was just saying a minute ago? Take your concentration units and turn them to conversion factors. Here's the conversion factor that always works here. That translates to grams per 100 mils of solution. Directly. So I can just put it right in. Straight in. So the part they're missing here is really mass of solid per 100 mils is proper. So 1.5% saline, 1.5 grams per 100 mils. Now I know how many grams come out every time 100 mils comes out. 1.5 grams, and that's how I can match it up to body weight, and I'm good to go. And if I'm giving a shot, it's administered in mils, right? Or cc's, cubic centimeters, or sometimes microliters, but I can make that adjustment. But then I can kind of correlate grams to that. Is everybody okay with that? Okay, we'll do a little bit of work with that too. And again, this is the part and I'm very diligent about this now that I understand it. I always try and make sure students understand the application where I'm working. Like where you're working, if you hear percent, that's probably what you're talking about. Not always, but if not, it will be specified. Sometimes you'll see mass per mass. That literally means, okay, that's how many grams per 100 grams. That would be normal. If you guys go out drinking, like you're done with me, you're having spring break, and you go, oh, okay, and you see 3.5% or 6% alcohol, that's volume per volume. That means 6.5 mils of ethanol per 100 mils of ethanol, and that's a pretty common thing too. But see, that's normal. The units are the same, volume per volume. These are weird because they're mass per volume. And so again, I just want to remind you, the top number is always the grams, bottom number is always 100 mils, and then you're good to go. Okay, so here we go. And then if I get used to this conversion piece, where I go, okay, I'm going to turn that percent into a conversion factor, then I'm going to have this solved. All right, so how many grams of sodium chloride are present in 250 mils of a 3.5%? And again, I told you this, but again, if you took an IV at the hospital and hanging on the bag, and it says this on there, 3.5%, nowhere on there does it say mass per volume. And that's why I'm trying to help my students. Like, if you're in a hospital, that's what they mean. Okay? So, enough of that, but you got the idea. I just want you to like zoom in on where you're at, like look around, what am I doing here, right? If I'm hanging out with chemists, then we're probably talking molarity, and then you know what that means now. Okay, and I'm gonna show you the other one. Parts per million, that's the other one you guys should be familiar with. All right, here we go. What do I know? How much do I have? I know this concentration, but as I told you, concentrations doesn't tell me how much I have, right? You could have the same concentration, but you could have different. By the time class is over, you'll have different amounts, right? How much do I have here? Good, I got 250 mils. A solution, if you want to say it that way. So you kind of have it in your head, yeah? The whole solution mix. I'm going to turn that into a conversion factor. Hopefully all together now we're going to go, oh, that means 3.5 grams of
saline solution.
saline. What is that stuff called? You can say that. Somewhat. You're being so vague. We have a chemical name. Sodium chloride. There we go. Sodium chloride. It's all true, by the way. You're nailing it. It's just per 100 milliliters. That's the key. That's your conversion factor. Like, you will have to memorize that piece off the percent. Okay, now let's set it up so we can cancel this out. What goes on the bottom? By the way, that's solution, right? 3.5 on the bottom. See? No, and I'm glad you saw it. I'm going to finish for just a second so everybody catches what you caught, because you might have seen it quicker than everybody goes. I want you guys all to pay attention. Is that going to cancel?
No.
No, and then how do you correct it? Flip it. It's still true. If there's 100 mils, you'd have 3.5 grams. If you have 3.5 grams of the 100 mils, it's still true, right? So I can just flip that. Conversion factors can do that, right? Cool. Perfect. We can. Now we can do an answer, right? The math is 250 times 3.5 divided by 100. It doesn't matter what order. 250 divided by 100 times 3.5. Whatever order, it's still going to come out, right? All right. You guys agree? I want to get some consensus in here. Give me this if you're okay. Good. You're getting some. They concur. Nice. Same idea. Now I'm just giving you the flip of the problem, just so you know how to work it both ways. How many mils is the same solution? What if I have to get 0.5 grams into somebody? Now I'm like, okay, how many mils would that be? So that's very realistic. It's not so much with salt solution, but with like a painkiller or something. It's like, hey, based on your body weight, you need a half a gram. How many mils should I pump into your body, right? Would that make sense? All right. So what's the setup? Where do I start? What am I looking for? What am I given, basically? Everybody getting that? 0.50 grams sodium chloride. And then my question is, how many mils? So I'm actually going to go to mils for sure, right? Then I use that like a conversion factor. What goes on top?
under, you know.
Yeah. .5. I know that I've done good if these cancel and give me the units I want, which it does. Math says 0.5 times 100, it's like 50 divided by 3.5.
How would you find 3.5 if you didn't do the first? That makes sense.
Where
If
was
I
it?
didn't know there was 3.5, where did you get it in a second?
Oh, it's right here.
Yeah, but if we didn't do that one?
Oh, no, it'd be a mystery. You have no idea.
Okay, good.
Because you got to have the concentration, or else you don't, right? You could have different concentrations of salt solutions.
Yeah, okay.
Thanks for asking. Anybody got a number for me? 14.3, is that good enough? Am I getting this around the room? People agree? Yeah? Good? Good? Cool. Yay. Make sense? All right. Just if you got, remember these, you can always click back through and see how they set up. I'm gonna do this one without this off the slide, and we're gonna talk about parts per million for a second, because like I said, apparently that's coming up some. Does anybody, you guys, a lot of you guys are technicians or working in it. Do you know where you've seen parts per million? She mentioned it, Paige mentioned it, I just didn't, I could have given you an example, but I wasn't paying for very good attention. No? Okay, we'll just do parts per million because it'll seal it out. It's another unit. I will tell you this, it's apparently showing up in something you're administering. I don't know, maybe ask today when you go to work or whatever, let me know. But for me, I always think about parts per million from the environmental chemistry standpoint, and it would be common to show that in newspaper articles and magazines because people will talk about Flint, Michigan, right? They released lead into the river or into the water supply, and they said it was found to have 400 parts per million, right? Or if you look and say, I always warn you guys about nitrites in the water, and they go, oh yeah, you can't ingest more than, the Clean Water Act won't allow you to release more than 5 parts per million of nitrite into the water. 10 parts per million nitrate. So it's very common around environmental chemistry. It is kind of like it sounds, but that's not very useful. It's a big calculation if you do it that way. So 5 parts per million nitrite means for every million grams of solution, I would have 5 grams of nitrite. And that would be semi-useful, but usually this stuff are aqueous solutions. And I'm like, what does that mean? That means I have to weigh out the solution now? So I'm going to give you the go-to conversion factor. You ready? Parts per million can be always translated it's milligrams per liter. Immediately. So now when I hear that about Flint, Michigan, I now know, if I picked up a liter of that stuff, right, I would get 40 milligrams of lead in my drinking water. Follow? If it said 40 ppm. Make sense? So now if you work the whole series, like if you're in environmental chemistry, I'm going to hold you just to one, but just for your interest, we've also got to where things are trace smaller. That's not really relevant to your field because you're probably not administering anything in parts per billion. That means for a billion parts of water, you'd only have 1. Right? And then there's also parts per trillion. And some of that wasn't even a valid measurement. So like I was in grad school when that parts per trillion, because we couldn't even measure things that small. Now we can. The reason it came up is because in the environment we had some releases into the water that were that small and we didn't think much of it, but then they started to accumulate in the fish. And they bioaccumulate and we're like, oh, that's a problem. Case in point is birth control pills, whether they're naturally excreted or they're just dumped down the drain, they end up in the water treatment. They don't always get cleaned out properly, so they end up in the water system. And then this, like below Boulder water treatment plant, they found out all the fish were female. And they're like, why is that? Well, because they're odd. The male fish are on a steady diet of birth control pills and they all feminized. So that was a problem. All of a sudden everybody got nervous. They're like, oh, we better track this. But we ourselves, and I always drink filtered water because of these sorts of things, but we're kind of on a small parts per billion, parts per trillion diet of the stuff we're putting down the sink because we can't get it all out. Hopefully it'll pass. Sometimes it bioaccumulates and it can be problems. Like somebody's taking mood-altering drugs that are prescribed, or they're just doing it recreational, whatever. But you know, I'm probably drinking parts per trillion of that. Someone's out synthesizing fentanyl. It's like, well, okay. I'm not trying to scare you guys. I'm just saying your liver's an amazing thing. It usually kicks it out. Not a problem, but it did become a problem with some things because of what they call bioaccumulation and the fact that these things play together. Anyway, that's kind of my area. Like I think about cleaning up water all the time. But with that in mind, I'll just show you how these conversions are really pretty simple. They're in thousands. So if that's a milligram, that 1,000 times smaller than that is a microgram. And 1,000 times smaller than that's a nanogram. And so that's what those mean automatically. So when I say, oh, there's a part per trillion, you know, I think that the new things are the fluorocarbons that are coming out. They're realizing that it's like, we can't get rid of this. Off our Teflon cookware and all that stuff. I don't mean to make your, I'm not trying to ruin your day, but it's just, it's a problem with water treatment. Be grateful we have one of the best water treatment systems in the world, right? People start, you know, dogging the Clean Water Act. Yeah, if you just open it up to make people rich, you'd have a lot more problems than you think. Anyway, enough of that. This is the one you need to know, so let's work with it. But this is just side notes, milligrams and nanograms, in case you do other stuff. But let's just do the same thing. First off, if I give you a concentration and tell you how much you have, you should be able to tell me how much is released. And then the other way is, hey, if I know the concentration and I release some volume, how many milligrams did I do? So let's do it both ways and then you're set. Okay? So, we'll do a two-step problem because this would be good for you to think back to how we used to do this. How many grams of, we'll do lead, we'll do this. So in other words, someone said, hey, the lead's contaminated with 20 parts per million. And I grab 4 liters. I'm just going to say, how many grams is that? So this would be a two-step conversion. This would be good for you guys. Again, what are we starting with? 4 liters. That's how much we have. So remember, concentrations are concentrations. Having 2 liters, having 1 liter, I still have the concentration. Just still doesn't tell me how much. It's the 4 liters it says. Oh, okay. 4 liters of this set concentration is so many milligrams in this case, correct? Next thing, this is no use to me for converting, right? What do I turn it into? Milligrams per liter. So once you get that down, and you just go there all the time. So there's your 3 milligrams per liter for this one. Grams per 100 mils for the other one. The first one is moles per liter. That's your 3 kind of things you got to get square in your head. All right. I'm going to end up saying grams when I get there, right? How do I insert that to get close? As is, or should I flip it?
Yes.
Flip it. You think?
No.
Oh, it's okay. It's worth making a mistake because you just see, hey, it doesn't cancel. So, by the way, that's called, these are called factor label method or dimensional analysis because they're trying to tell you if you watch the dimensions, they'll work. If they don't, it's telling you to fix the math. That's the whole point. So it's kind of cool. I'm going to flip it. That's 20 milligrams of lead 2 plus, right? For every 1 liter of solution, right? Nice. Now what? Yeah, I got to change to grams. How many milligrams are in a gram?
1,000.
Yay, all right. I love that. Where should that go? Top or bottom?
Milligrams.
Yay. 2 steps even. Fancy. Fancy smancy. It's kind of a cool conversion unit, right? Or method, right? So now I'm going to go do the calculation. 4 times 20 divided by 1,000, right? Just all in one string. You don't have to get anything equals and then re-enter. Just do it all in one string. And this we could even do in our noggins if we were feeling feisty. That's a 4. Here's some cool math tricks. Every 0 on top cancels a 0 below. 4 times 2 is 8 divided by 100. 0.08. Yep. That's how much lead would be in there. If I could get the lead out. Never heard that expression. Today I'll show you how to get the lead out. For reals. Ooh. It's a good demo. I'm going to do a demo of, certainly, but maybe I won't pull the lead out because then I got something I got to clean up. It's different. Feel good about that? The other variation would be going like this. All right. Here, somebody give me a concentration. I don't care. Any concentration. 10? 25. Okay. It's 25 part per million. What's any chemical that comes to mind?
Calcium.
Which one?
Calcium.
Calcium. Okay. That's nice. So this is good news. We needed some good news. If it's floating in the water, you see why I do that? We're going to figure out how much is in there because we're going to put it in our milk and fortify our milk and make our bones strong. This is good news, as opposed to all that other stuff I was scaring you with. All right. How many liters do you have today? Or milliliters? What do you want to do? 4 liters or milliliters? Oh, yeah, 4 milliliters. Cool. All right. Do it that way. Nice. I'm good. So, I've got 4 milliliters of the solution. How do I rewrite this conversion so it's got some sort of conversion factor? 25 milligrams of that per 1 liter. Okay, cool. So how would I put that into here? You want to turn that to liters first, maybe? Okay. Milliliters on the bottom, liters on top. Which would be true? What number would I put down here? 1,000. Cool. So I'm almost there. Then what? Now I'm ready to put this thing in. Which way should I put it? Because I want to end up with milligrams, right? Where I'm trying to end up. Liters on the bottom. Cancel 4 times 25 divided by 1,000. Final answer. So 100 divided by 1,000. 0.1. Not much calcium in there, but a little. Stuff. That's all your variations of this that you guys can practice on. So I might alter your homework. I might give you just a little extra to work with the PPM just to get back and forth on there. So I'll write you a little side set or something to practice with.
That'd be great.
Yeah. Okay. Good stuff. That's kind of the math of it. All right, so now you kind of know, and again, we got to get this down pat. You ready? We're going to walk through them again. Molarity means what? Big M means moles per 1 liter. All right. Percent, as we talk about in the medical field, okay, I'm going to do, administer percent, 0.1, whatever, pain reliever, right? What does that mean? Grams per? So it's different. No, it's grams per 100 milliliters. Make sure you get that right, because that's a little unique, right? But percent always should clue you in 100. When I hear a percent, I'm going 100. Go 100. Percent always means per 100. And then parts per million means right there. Milligram per liter. So the moles and the parts per million are per liter. The percent is per 100 milliliters. And then you're way off and rolling if you can remember all those little parts. That's the keys. That's why it's kind of got a unique name. So the properties that we know about, there's a lot of them, but the ones I'm going to focus with you guys are boiling point, melting point. I should say osmotic pressure because that'd be relative to you guys. I don't know if I said it or not, but I should. But vapor pressure is the other one. Okay? So my point is this. Relative to water, I know that this has a higher boiling point. I know that it has a lower freezing point. I know that it has less vapor pressure. I know that it has more osmotic pressure. I don't even care what's in there. I know something's in the water. It's going to raise the boiling point, drop the freezing point, it's going to drop the vapor pressure, and it's going to create more osmotic pressure. You with me? So now I'm going to explain that the best I can. Going to kind of hand wave that. So here I've got water and it's a salt solution. You see it? I got the salts all dissolved. There's a lot more water than salt. Always is, right? Because remember, salt never breaks apart because it's a strong ionic bond. It never breaks by these little hydrogen bonds grabbing it unless there's a lot of water to surround it. Then it breaks it apart fine. Remember, hydrogen bonds are like order of 10 kilojoules. They're strong, but not that strong. Sodium chloride is bound together on the order of 200 to 1,000 kilojoules. Pretty strong. So I got to get a lot of water to get it separated. But anyway, that's just common, and we know salt has a limited solubility in water. If I pour too much salt, I just get salt poured down to the bottom and it no longer dissolves. But once it's there, let's think about this water ready to boil. Okay, in order to boil, I got a couple things that have to happen. I got to have enough energy, which I add in the form of what? How do I get it more energetic, moving more? Heat. Raise the temperature, it has more velocity, right? So that's one way to get it to pop out of there. Makes sense. The other one is I drop the pressure. Okay, so the pressure over the top is what holds it in too. Under high pressure, water boils at different temperatures. As you lower the pressure, it boils at lower temperatures. Okay? But the other trick is this, colligative property. So that water is about ready to take off, and it goes, oh, dang, there's a salt molecule, and the salt molecule grabs the energy off of it, and the salt's not going to boil, so it just heats up the salt. So now that water has to start all over again. It's like, oh gosh, now I got to go by to the heater, get my energy back, and I'm like, okay, I'm ready to go. Woo-hoo! And then, boom, hits a chloride ion. Loses its energy. So does it make sense if I dissolve things in a solvent, that solvent can't boil the same because it's going to bump into the things and lose energy. So now to bypass that, I got to heat it up even more so I have enough energy to kind of knock into the salt and get out of the water. Does that make sense? So generally what we're going to say then is if the concentration is going up, the boiling point's going up. Always. Okay? Now, we also know that vapor pressure is this kind of the inverse of boiling point. Remember vapor pressure? That's just, this water has humidity above it. It's like living on California in that little world inside there. It's like being by the ocean. Like it's humid in there. Does that make sense? That's vapor pressure. There's some water that is already boiled. It's kind of hard to explain, but basically there's some water that kind of, we'll just use the term evaporate. You guys got that. That makes sense? So if the boiling point's going up, though, something doesn't boil very easy, then there's less likely that it's going to turn vapor early. Now think about things that have low boiling points, like alcohols. Like this stuff here, the alcohols or gasolines, and you go, oh yeah, when that, I can start to smell it already. It turns to gas very easy, right? So, this is just an always thing. The boiling point's going up, the vapor pressure's going down. So I go from something that has mostly dispersion force, very low boiling point, that has a lot of vapor pressure, to something that has dipole forces, which is a little higher boiling point, little less vapor pressure, to something with hydrogen bonding, like water, right? It has a lot less vapor pressure. Does that make sense? As I get higher and higher in boiling point, the vapor pressure is going down, down, down. So those are hand in hand. So now you have that kind of locked in. You guys, take a minute, process this. Now I'm going to tell you. Concentration's going up. What's the vapor pressure doing?
Going up.
Down. Show me. Right. So there we go. Both. Yeah. Thank you. I appreciate that. It's good. Okay. Now we're going to talk about melting point. So this is a little different concept, right? Because in order to, and I kind of think of it more like freezing, right? If I start to freeze something, I start dropping the temperature on it, right? So here's my water molecules, and I start slowing them down. They kind of just get closer and then the hydrogen bonds can grip, and then it locks into a solid state. And if I can heat it up, I can break that apart and it'll start spinning freely. Does that make sense? So if I lower temperatures, things are going to tend towards freezing. Now I'm going to put a salt in the middle of that. Kind of like this. I'm going to put salt in the middle of it. Right? It's dissolved. You know what I mean? Right? What does that mean then? Now all of a sudden I'm having problems getting together. Because what's in the way? The salt. So now I have to cool it even more so that it'll still kind of get close enough, can kind of bypass the salt and get that hydrogen bond going, and just like, okay, if I have any energy, it's going to want to start moving and get away. But if I cool it more and more, it'll finally get close enough and it'll actually lock. So what I say is if the concentration goes up, the boiling point, freezing point goes down. So when it's ice outside, we start pouring salt on it, and the freezing point drops, and all of a sudden it turns back to liquid. Right? Solute molecules, that's solute, the stuff that you dissolved in there. And again, it's colligative. I don't care if it's salt or sugar, I don't care what it is, it's just how many. Disrupt formation of the solvent-solvent intermolecular bond, i.e. the crystal, the solid. It's freezing. until kinetic energy is slowed down enough that the solvents can settle into a crystalline lattice and freeze. Forcing it, sometimes it forces the impurity out of the structure. That's kind of cool. So this is kind of fun. Somebody's taken these pictures of this purple salt that's gotten frozen, and you can see it starting to get forced out of the pores, which is kind of cool. Kind of helps me understand a little bit. Like, when that ice starts forming, it just kind of sometimes just shoves the impurity out. We use, sometimes we use that trick in chemistry. We do what we call a freeze-thaw cycle to purify things. So we run them through freeze-thaw, and then we knock the impurities out. Oh good, I got osmotic pressure, because that'd be relevant to you guys. Kind of the medical, whatever, dentistry type stuff. Osmotic pressure, right? So osmosis, if you don't understand, is if you have membranes that pass solvent but not solute, like their size is okay to pass solvent. Now they don't always necessarily have a hydrophilicity that passes solvent. So like your cell wall, right? What's in your cell wall, by the way? That's a good question. That might show up on a test. Maybe. Phospholipids. Oh, whoa. Okay. Phospholipids, right? They create a cell wall. That cell wall is open enough that water could pass through there. It doesn't want to because it's water hating, right? It has a big lipid piece to it. But sometimes under the right pressure, it'll pass through, right? That's called osmosis. And the reason that works is you basically get one concentration on salt one way. Like if you get a salty side to it, like the innards of the cell, which have all the cell pieces, just remember, once again, it doesn't have to be salt. Anything dissolved in the fluid, right? Then the osmotic pressure wants to force the water towards that to dilute it. That's a natural flow of the universe. That's kind of weird to me. But it's what it's based on is something called entropy, which is that basically when I have charges together in a concentrated salt solution, they'll naturally want to move apart. And to prove it, if I take this sodium chloride and just drop it in water, it will dissolve itself. It'll just start pushing in parts. It'll get as far apart as it can in the solution one. It'll distribute itself throughout the solution. That's entropy. Now, if I can't get it any farther apart in the solution because it's already dissolved, but I have the ability for water to pass into that, that will distribute that charge more. And that's what drives that. So here's what you need to know. If the concentration's going up, the osmotic pressure's going up. So the saltier I get here, the more the water wants to drive into this. Right? The saltier this gets, higher concentration, osmotic pressure wants to drive towards the salt. It's like potato chips. All right, I get my salted nuts. That sounds good. Yeah. Then I got, right? I get all that salt in my diet and it ends up inside my blood vessel. Right? And then the fluid that's in my interstitium, that's the stuff around your blood vessel, which carries liquid, right? Because I'm kind of full of liquid. It passes into that blood vessel. And the blood vessel goes, whoa! I got high blood pressure. Right? So I need to either water down or quit my salt intake, something. Does that make sense? Okay. And sometimes we do weird things with that. You know, you come near a slug, you hate slugs in your garden, you just put salt on the outside and they go, oh, water's leaving me, and they just shoop, and they're gone. So that's kind of a weird thing. I know. Not such a thing in Colorado. We're not like a sluggy place. Oregon, you guys been out in the northwest? Yeah. Go hiking out there and there's like colored big slugs everywhere. Oh, crazy. Good? Now again, I'm just telling you, it depends on the number, not the ID of this stuff, okay? So now we have it. I'm gonna let you launch off to a little break. I just want to see how we're doing. I just got to get these things right. So we got 4 things we're doing. All right. So I'm gonna always raise the concentration. I'm always raising the concentration. You tell me which way things are going. You ready? Okay. I'm gonna raise the concentration. What's the boiling point doing? Going up. Cool. What's the melting or freezing point doing? Going down. How does the melting point compare to the freezing point? Same, thank you. That's one you got to kind of, if you forget that sometimes, just kind of put a note to yourself, like, hey, freezing is boiling, and it's at the same temperature. Yeah, freezing is at the same temperature as melting. I would be lying to you. I did lie to you. I said it's the same thing. It's not the same thing. When I freeze something, it now drops in energy. When I melt it, it now gains in energy. I just can't measure it with the thermometer. That's why it's mysterious that way. So just heads up. But when I say freezing point or melting point, right, those are the exact same number temperature things. Water freezes at 0. Water melts at 0. Weird. I know. So that particular event of changing state, it's hidden from the thermometer. It's called latent, which by definition means hidden. It's latent heat because it's hidden from the thermometer. I can't measure it with a thermometer. So when I start boiling water and I put the thermometer in, I'm pumping energy like crazy off the stove into it, but the thermometer just stays stuck at 90 degrees in Colorado, right? You're like, what's going on? Why aren't I measuring more energy? Because my oven's going crazy here. The water's like boiling, and I'm like, what? Why am I not measuring more energy? Well, that is bond breaking events, right? I'm breaking the hydrogen bonds. But the water that's spinning at a certain temperature, which is 100 or 90, is now moving at 90, and the thermometer says, I'm still at 90. It's kind of strange, isn't it? This is weird, isn't it? That's one of those weird science things. I'm sorry, I went down a whole rabbit hole. Let's come back. If the concentration's raising, what's the osmotic pressure doing? The osmotic pressure going up. If the concentration's raising, what's the vapor pressure doing? I got some convinced people here. You guys know over there? Okay, good. Thank you. All right, take a break, and then we'll get back and we'll kind of work on that piece a little bit more. Okay? Maybe I'll turn on let's kind of get this idea down. You walk me through that if the concentration's going up, right? How the boiling point's going up, osmotic pressure's going up, vapor pressure down, all that good stuff, right? So that's good. But I want to show you kind of the big kind of curve in the road that a lot of students get messed up on, okay? So we're going to do this together so I can just show you. I'll just show you. Okay? So why don't you come up here a little closer? We're going to work together on this for a minute. Maybe we'll use this as our little notepad. Come see what we're doing. This is a conductivity meter. So it literally measures how much, well, this would be good for you to know. It'll only measure ions, okay? It'll only measure ions, really, in solution. So I could have something that's a non-ionic substance and it won't necessarily register on this. But as long as it's ions, it'll register. But the thing I want to show you is kind of the intricacies of how salts break into multiple parts. You with me? So salts breaking into multiple parts, that's your hint. So here, I'll give you a little fruit dust. Come on in. There you go. Blinded here. In fact, you want to help me with some notes up here for everybody? Sure. Okay, cool. That would be awesome. Is everything behaving? I didn't behave. Okay. All right. So here's what we're going to do. This is a conductivity meter. So this is kind of instructive. If I had this in pure water, it might show. I should have brought. I don't know if I got a pure water one. I think I burned it for something else. Oh, I do. Cool. Nice. We'll call this pure water. This is out of the school system, which actually purifies all the ions and deionizes it. The nice thing is if it's not pure, we can check it with this conductivity meter. And if it's the purer it gets, the less conductivity. And we're just going to use numbers. So first off, tap water, if you want to write that on the board. And somebody do my reporting here. What's the measurement you see on there? Anybody?
393?
So tap water actually has 393. So I don't know what that means. Yeah, so 393. And if you want to know these units on, it's kind of interesting. It's micro Siemens per centimeter. The Siemen, the S-I-E-M-E-N, that's actually a measurement of how much conductivity goes through a centimeter distance. So they're just passing current through a centimeter distance. And it's saying, I have 393 conductivity units. Okay? Now I'm going to put it in really clean water just to see what our tap water is like. Again, I'm not trying to terrify you guys and have you awake all night, but you guys are fully aware that our tap water has lots of salt in it. It's just normal. That would be normal anyway. It's super clean water. You would hope to have some in there. So what we consider to be clean is 13. And so I might be able to clean my glassware even better, maybe drop it down to 8 or 9, but there's going to be a few ions. But we have a lot of salt in the water, and most of it's innocuous, no big deal. All right, so here we go. I'm going to now start putting some solutions in there. So let's start with this one. How about, they're all the same concentration. So if you don't mind writing the concentration down, we could do, go ahead, sodium chloride. 0.005. And we're going to call it, I think this is sodium chloride. This is just table salt. And by the way, that's a big M. That's 0.005 big M. That's molarity. Right? You ready? So there we go. In there. Somebody's got to be up here recording. All right. Ready?
540
540.
or 2?
Yeah, close enough. We'll call it 543. That's good. All right, cool. Now, and this is kind of the main point of this whole little conversation, I'm going to go to something. This is 0.005 iron 3, 0.005 molar, sorry. It's iron 3 nitrate. Somebody make sure. So iron 3, so Fe. And then NO3 is the nitrate piece. So what's the charge on a nitrate? -1. So how many nitrates would attach to an iron 3 if they're -1 apiece?
3.
3, perfect. So it's iron 1, NO3, 3. There you go. Perfect. Thanks, Dallas. Put you on the spot there, but you're doing great. Adjusting. Make sense? Now, I'm just going to ask you before I put it in there. Same concentration, but it's iron 3 nitrate as opposed to sodium chloride. What do you think the conductivity is going to do, and why?
How many high?
Why? Nothing complicated. It's just simple. Because I'm gonna reword the. Can anybody define colligative one more time for me? Because I was very specific. Colligative says, do we care about the parts? It's just how many parts, right?
Yeah.
So now I'm going to just reword that. Is sodium chloride has how many parts when it falls apart in water? 2. Sodium chloride aqueous is sodium plus floating around and chloride minus floating around, correct? You with me? What about iron 3 nitrate? How many parts? 4. Yay, so we'll see. We'll see how good the solution is. This has been hanging out a bit now if I saw a little bit of a kind of a decomposition, but if it's twice as many parts, what should the conductivity be?
Higher.
Twice as high at least, but we'll see. We're close.
1,000.
We're at 1,000. It's pretty close. Twice as high. Does that make sense? Okay, cool. Now let's see if this measures, I don't know, it might be able to measure non-ionic things, we'll find out. I should know that, but we'll find out. I'm gonna put, do I got a non-ionic something? Yeah. Here's acetic acid, which is pretty much a one-parter.
138.
Okay. That's one part. It's 0.005 molar acetic acid, which in essence is really one molecule floating around. So it's 0.005 moles per liter. Okay, thank you. Now we'll sit down and we'll talk about that a little more. Is that making sense to people? You got to think about how many parts go into water before you start talking about boiling point raising and lowering a little bit. So I'm going to just show you some ways to kind of get that clear so you don't get confused by that. And then we'll rank out some solutions. All right. So this is awesome. You guys, I can't even do this, Chem 1 and Chem 2 students, but you could do this. That's the acetic acid. Now, it's carboxylic acid. What's the real name? It's not really acetic. That's a crappy picture of it. Oh, there we go. Who's got the root name? Just by looking at that structure. Just give me a piece of the root. Close. Try again. Eth something, right? This is ethanoic acid is what it's called, technically. How did I know that? How many carbons I see? 2 carbons. And then there's the acetic acid piece. Now you haven't learned how to name that, but you just basically throw on oic acid on it. So this is ethanoic acid, as opposed to propanoic acid, butanoic acid. Follow? Okay. This, in this particular case, is what's called a weak acid, so it stays together in water. It barely comes apart. So, this is the part I want to teach you. The things that barely come apart, like sugar and a lot of your organic stuff, like ethanol, methanol, that sort of thing, I would only count those as one part because they don't break into parts. So if I'm trying to look for parts breaking apart, look at the structure. There's kind of a commonality versus a structure like this. And by the way, if I did the formula, it would look like this. C2H3O2, and then they might even put the H at the end to make sure you know it's acidic. So if I said, oh yeah, I've got 0.005 molar this, and I'm comparing it to 0.005 molar this and 0.005 molar this. You guys understand, I'm trying to teach you how to kind of look up there and go, oh, there's parts. I gotta account for the parts to know how the boiling point's changing. Now do you see what I'm doing? Okay, step 1, if it's ionic, then you gotta figure out how many parts. And we already did that, like almost first day of class, first week of class, we're like, here's a structure, how many different polyatomic ions, how many atoms, right? So whenever you have polyatomic ions, that's a single part that splits out, right? How many of those do I have? 3, and how many ions? That's a total of 4. So in terms of the real concentration, 4 parts. 0.05 times 4. That's a lot more concentrated than 0.05, isn't it? And hence, the number is way high. How many parts in here? Okay. 0.05 times 2. I'm sorry, I know that's confusing you. I apologize. Let me scoot over a little. You're like crazy man. Why is 1,000 times? I'm talking about the concentration. 0.005 times 4 equals 0.020 molar. Take your concentration times the number of parts it splits out in water, and that will give you the colligative number that's important. Higher concentration, higher boiling point. All right, here we go. This is 0.005, and that's borne out by this being the highest number on here. This is about half of that, because 0.05 should be times 2, because there's 2 ions, and so really the concentration is, yeah, that bears out, doesn't it?
You said that answer is colligative what?
So that's how many parts are floating in the water. That's called a colligative property. So, but what I'm trying to help you get up to speed on is I could draw a million different compounds. And then you have to ask yourself, does it break into parts? And I'm going to give you the simple way is look for metals or ammonium. Metals or ammonium signal an ionic compound, and I have to think about it breaking. If it's not ionic, I don't have to think about it breaking. Did everybody get that? Okay. Look for metals, or the sneaky one, because it's a non-metal ion. Then I got to start thinking about parts. All right. I look at a structure like this. Do I see a metal? Nope. Do I see ammonium? Nope. It doesn't break into parts. Huh? Now you tracking? So I just have to say that's times 1. Kind of half of this one. Close. 138, right? Kind of about, a fourth. You with me? It's quiet in here. Okay, do this for me. Just help me out. Does everybody understand what I just did, or you're like, or hey, I get it, not at all? Help me out. Where are you at? Give me a where are you at? Where are you at? In the middle. You're middle. You're not okay. Okay, so here we go. We're gonna start doing this. Ready? I'll set up a new set, and this is probably on the slide. It'll come up pretty quick. We already know this, right? This is what we just worked out. Okay, here we go. We'll do these. You ready? We're gonna analyze them. So the things I'm looking for are metals, right? I'm thinking about ionic compounds. Everybody understand that? So think about this. When I say I have ionic compounds like this, if it's ionic, it's split into parts. If it's not split into parts, it looks like this. And I'm very, very safe to assume, I can grab any one of these. When I take a salt and drop it in water and the water goes clear, I've split it into parts. So anytime I have a salt and I have an aqueous after it, it's like, oh, it's split into parts, or else it would be solid in the formula. You with me? And that's what I was saying earlier. This iron was sitting around enough. For some reason, something's precipitating. See how cloudy it's getting? That's a salt that's somehow recombined. I'm not sure what it is. I have a theory, actually. There's enough CO2 in the air, it's getting in there and making carbonate over time, and it's making iron carbonate starting to fall. Okay? In fact, I could probably prove that. Here's some sodium carbonate. So if I just want to accelerate it, I'll just drop a lot of carbonate in there and you'll see the iron start falling out. Hopefully, we'll see. We'll see. Oh yeah. Whoops. Can you see that? It looks like it's starting to cloud up in there. It's not thick. See it's starting to cloud a little bit. doing its thing over the class. That make sense? Okay, here we go. With that in mind, let's go up on the board right now. Well, first off, pure water, okay, that's the original boiling point, it's 100 degrees. We'll just say that, correct? Now, when I look at the structure, do I see any ions? I see metals or ammonium? Nope. So how many parts does that dissolve in there? 1. So when I say it's 1 molar of glycerol, it's literally 1 molar of glycerol as it pertains to raising the boiling point and dropping it. How does that compare to this, though? Is it higher or lower? Higher, because it has some concentration, right? So boiling point's going up. All right. What about this? How many parts here? 2. So it's really not 2 molar, it's really, 1 molar, it's 2 molar. How many parts in here? 3. So it's really 3 molar. And so this will have the highest boiling point solution. These are all aqueous, by the way. I should have put that in. That'll help you a little bit. They're all aqueous. Follow? So here we go. Pure water. No parts. 1 part. Oh. Raise it a little bit.
Why does pure water have no parts?
Well, because pure water has no parts. It's the solvent.
Because it's the solvent.
It's the solvent. And I apologize. These are all aqueous solutions. AQ. That's this dissolved in the liter of water. That's what we're dissolving to a liter with water. 2 parts. Oh yeah, temperature's going up. In fact, it went twice from that one. As we thought. The raise was 0.5. The double would raise it to 1. 3 parts. Is that? Oh yeah. See it? All right. You ready? Now we get practice. So, we're going to leave you with this one. We're going to work on that. We have solutions. You got to figure out parts. Again, I'm kind of cheating for you, and I shouldn't be doing it, but look, I want you to break out the parts here based on the structure, and then you tell me what solution it is. See how we're doing that? Does that make sense? That's what we're talking about? And then we're going to figure out what's in it. And anytime, this is carbohydrates. It's from our little carbohydrate family. But either way, when you look at it, do you see any ions, nope, so it's 1 part, so it really is true concentration, correct? All right. So here's what we're going to do. We're going to work on that. I'm going to cut out this little practice cheating part for a second, and then I'm going to let you work on these because I don't really think you need that. I really want you to have that skill set there. Just bear with me. You guys can start ranking them out here. And I'm going to have you kind of work with your groups and work on them. I'm going to change this set a little bit. I'm going to just have you do this. Instead of looking for the highest or the lowest, I'm going to actually just rank them out. Just rank them out for me, okay? Just put them in order from high to low. Okay? Yeah, this is great. All right. So, you ready? You guys can work on number 30. Just rank it from high to low in terms of boiling point. Just put the letters up in order. And you can show the work. That would be awesome. Show the parts. So we're going to go from low boiling point. And then we're gonna go letter. And then you're gonna just go ahead and do the concentration calculation so I can just see how you're doing that. Is that right? Perfect. That's you guys. And we're gonna have somebody work right here. And you're gonna do You four ready? You can do 31. We're gonna go from vapor pressure. Ooh! We'll go from high vapor pressure to low. And then just show me your concentration calculation so I can see how you're counting pieces. Alright, so just put your letters in order. Sound good? A little more room to work. Perfect. Alright. Give you two a break over here. The rest of you five will work over here. And you're going to work on osmotic pressure, not the second highest. We're going to just rank the whole osmotic pressure from low to high. Okay? And away we go. You will be off and rolling.
I think you're just saying who was.
Pretty darn good.
Yeah.
What is that?
This is one.
Contact.
0.1.
Yes.
Something calculation.
How did you calculate this? That's what I mean.
Okay.
Yeah, sorry. What are you doing?
So that's okay.
How did we calculate our concentration? Is what I'm saying.
Okay.
Yes.